Hi, thank you for joining me for this discussion of iteration with purrr. So I am Jason Graham. I'm a faculty member at the University of Scranton, which is in Pennsylvania in the Northeast region of the United States. So what I want to talk to you about is iteration in R, specifically using purrr. Which is a package that is part of the tidyverse family of packages. So I'll say more about that later. Basically, what my goal is to cover is a little bit of background about iteration in R using for loops. I'll say some more about that soon. And then cover purrr, which is another approach to doing iteration in R via functional programming paradigm, as opposed to sort of what is more conditional in languages like C and Fortran. So what you'll learn is about purrr, and then I'll try to show you some applications. I'll just point out that there are some very useful references for this material. R for data science is sort of an introductory level text that covers this material. Advanced R by the same author is covers a lot of the same material, but at a slightly more advanced level, explaining a little bit more about what's going on under the hood. And then, of course, there's documentation for all of the R packages and functions that we'll use. Just as a point, the R for data science and advanced R, and of course, our purrr documentation are all freely available on the web. I have included some code in this lecture to illustrate the principles I'm talking about. And this is all available to you on a GitHub repository that you should be able to access. Just one point: to click on these links, you seem to have to be in presenter mode for the slides. Okay, so I'm kind of assuming that you're coming to this with some previous background in R and even some use of the tidyverse. So specifically, I assume that you have some familiarity in working with vectors, lists, data frames, the typical R sort of data structures, and then using some of the utilities for plotting and data manipulation in R via the tidyverse packages such as ggplot2 and dplyr would be useful. I think you can still probably get a decent amount out of this lecture even if you don't have that background. It would also be useful if you have, for the applications that I'm going to show, some background in basic stats, but I'm going to try to keep it fairly simple, although I have included some more advanced examples in the code that I've made available on the GitHub repository. So our main theme is iteration, repeated action of some task. Loops are a very traditional way in programming to conduct iteration, to carry out iteration in programming. Loops are among the many conditional processes that are available in a programming language. So why iteration? A fundamental principle, one of the fundamental principles of good programming practices is to not copy and paste code. If you find yourself copying and pasting code over and over again that does essentially the same thing with maybe just a minor change, then you want to look for something like loops or the use of functions in order to avoid copying and pasting. Copying and pasting is, first off, not a good way to spend your time. It's not productive. And it also leads to places where there can be errors, bugs introduced in the code. So in order to minimize problems, try to reduce copying and pasting. So how do loops specifically help with this? Well, the basic idea of a for loop, which is specifically the type of loop that I want to talk about now, is that you repeat a specified action some predetermined number of times. So this is important to distinguish for loops from like while loops, which are can iterate until some logical condition is met. With the for loop, you say, I'm going to do X in number of times. Okay. Now there's a couple of different subtleties that relate to what you have to do before you start a for loop, specifically whether you need to initialize a sort of storage container to contain your the results if you want to save the output, or if you just want to, or if you don't care about saving the output, then you don't need to do an initialization. But I'll say some more about that later. So let's say, for example, that we have a container that holds 3 numbers. And what we want to do is multiply each of these numbers by 2. Okay, a for loop is a perfect way to do this. Let me show you an exact illustration of this using R specifically. So the general syntax for a for loop in R is the keyword for. You need a vector, a container for the items that you're going to loop over. Okay, so then for each item in the container, you perform the action on whatever that item is. Okay, so here's an example. I have my keyword for. I have a container that stores numbers 1, 2, and 3. As I iterates through this vector container 1, 2, 3, I'm going to print a multiple of 2 times the item in the container. Okay, the curly braces are kind of bracketing what is the action that I'm going to perform. So this is sort of the inside of the for loop, if you will. Okay, this shows the output. First I is 1, I'm going to print 2 times 1, I get 2. Then I is 2, I'm going to print 2 times 2, that's 4. And then I is 3, I'm going to print 2 times 3, and that's 6. And that's exactly what we wanted to do. Okay. Back to a previous comment. If I would have wanted to store these results rather than print them, then I would have needed to initialize another container to store the results, a container of the same size as the number of items that I'm going to iterate through. Okay, you really want to avoid adding elements to a vector in a loop that hasn't been initialized with the appropriate size first. This will cause major performance issues, especially for large size vectors. Let's do a little bit of live coding here to illustrate, again, the for loop idea that we've talked about in R. So specifically what I want to do is to show you this idea about the initialization or pre-allocation in a for loop. So let's create a new R script here. And again, create a loop that takes 3 numbers, 1, 2, and 3, multiplies each one by 2. Now this time, rather than printing them out, I want to actually store them in some kind of container. So since I know I have 3 numbers that I'm going to be iterating through, in other words, the vector that I'm iterating through has length 3, I need to pre-allocate a vector with 3 elements. I also know that the output's going to be numerical. So what I can do is create my output as a numeric vector of length 3. Then this is pre-allocated. Let's print out what's here. And it's just 3 numbers. Doesn't matter what they are. Okay, now we'll do for I in 1, 3. I'm going to store in the output for each index the multiple of the value. And when I run this, I should have changed what's contained in my output. And it does indeed store the values 2, 4, and 6. That is 2 times 1, 2 times 2, and 2 times 3, respectively. Okay, now that we've kind of talked about for loops a little bit, I want to move on. So for loops are actually really powerful, and you can do a lot with for loops. There are many, many applications for for loops. They're one of the key components of programming, along with other conditionals like if else, and while loops. But there are also a lot of situations when for loops, using for loops is not the best way to ensure that your code is clean, concise, bug error free, and reproducible, easily reproducible by others. Functional programming is another programming paradigm that allows for iteration via basically the use of functions and function composition. Purrr, the package that's part of the tidyverse, implements or facilitates functional programming in R. Now, in my experience, in things that I do, one of the major benefits of the functional programming paradigm, and specifically the use of purrr, or at least the purrr philosophy in R, is that it makes multiprocessing parallel programming a lot easier than trying to do the same sort of thing with for loops. So, keeping with the spirit of good programming practices, I want to spend more time with the purrr package than with just the basic for loops in R. So here's essentially the idea. I have several items that I want to apply a function to. Within purrr, there are a family of functions, the map family of functions, that allow this. So here's a simple example that accomplishes the same task that we did with the first for loop that we looked at. I have a container of numbers 1, 2, 3. I have a function that takes an input, multiplies it by 2. Map 1, 2, 3 to the function, multiply by 2, produces a list that contains 2, 4, and 6, the same result, essentially the same result that we obtained with the for loop. Now, I should say that map automatically creates an R object in which to store the results. I didn't save that by assigning it to a variable, but effectively that's what happened. The second point is that map in and of itself produces a list object for the results in R. So at times that may or may not be desirable, and we can come back to that point in a minute. So just as a sort of hopefully more concrete illustration of what is going on under the hood, what map does is map is essentially a function in purrr that takes as its input to apply some other function to. What does it do? It essentially element-wise applies the function f to each of the elements that's contained in the first input. So map maps the function to the input and produces a result and stores that in a list. Now, like I said before, a list may not be for a particular situation, a list may not be the best way to contain the data that you want to use in R. So within purrr, there are sort of variations on the map function that can store a logical or Boolean series of outputs, characters, doubles or integers, and even actually data frames. So let's actually go to R and pull up the help documentation on this map family of functions and see what we can learn by doing that. Okay, so what we want to do is look at the help documentation for the map family of functions. So here I have this script, which I made available to you. The first thing I do is load some packages. I specifically load the tidyverse package, and purrr, which is also a package, is loaded whenever tidyverse is loaded. So if you, just as a reminder, if you haven't already installed this package, you would want to go to the packages tab, do install, find tidyverse, and then click on install, which I'm not going to do because I already have it installed. And then I've run this line of code to load the tidyverse and hence our package. For the purposes of reproducibility, I have set a seed. This is not necessary, but if you want to get the same exact output that I get, you'll need to set a seed. Okay, so question mark map calls the help documentation, and here it is. Map is a function in purrr, and then you can see map always returns a list, but then there's map LGL for logical, map int for integer, map DBL for double, map CHR for character. So these all return some type of atomic vector, which is sort of a simpler object than a list, because an atomic vector can only contain all elements of the same type. So you can't mix numbers and characters in an atomic vector, but you can do this in a list. So lists are more complicated in some sense. And then there's also data frame options for map as well. And I will illustrate that soon. So what's very helpful about this documentation, it explains the functionality of the various map family of functions. That is what input is expected. And then, of course, as always, the most, at least initially, useful part of the help documentation is a series of examples that you can try out. So make sure that you have tidyverse or at least purrr installed, load that library, call the help documentation. Okay, so I'll get to some examples of using this in a second, but let me pause on RStudio and go back to our slides to introduce a little bit more background. Okay, so we had previously used map to sort of reproduce the task that we did with the for loop, that is multiplying a sequence of numbers by 2. And for the basic map function, the output was a list object. So here is an example of a use of another map family of function, map underscore DBL for double. So this is going to, instead of outputting a list, output an atomic vector of a numeric class. And so this can be useful if you know in advance that all you want in your output is numerical values for reasons that we kind of hinted at before. An atomic vector may be somewhere to work with than a list. So here's another example where I have, in fact, a data frame that's just some simulated data. It doesn't have any particular meaning with 4 numerical columns. What I want to do is compute the median value of each column of data in the data frame. So map underscore, I know that the median is a numerical value. I know that the data stored in the data frame and each column in the data frame is numerical. So it makes sense to compute the median, and it makes sense for the result to be contained in an atomic vector with just numerical values. So I apply the map underscore double function to my data. And what I want to do is apply the median function to each column in that data. And this is what the output looks like, and thus provides a method for achieving our data. So how would you do this with a for loop as opposed to the map family of functions? So we know that there are 4 columns in the data frame. What we want to do is loop over the column index for the data frame, and at each time compute the median for each column of the data frame individually. Now, depending on what you want to do, if you wanted to store those results, as we've talked about before, you would have to initialize an atomic vector of length 4 in order to store the results. The map family of functions applies a function to an input. In other words, it applies a function of one input variable to whatever the input happens to be. As I'm sure that you are aware, there are situations when you may want to apply a function that takes multiple inputs iteratively. And there are variations on the map family of functions. For example, map2 and pmap that can take either 2 for map2 inputs and apply a function of 2 variables to those inputs, or pmap can be applied to an arbitrary number of inputs. It does take some getting used to work with pmap. So basically what I'll do is allow you to, or point you to the documentation and the examples contained therein to sort of figure out how to use pmap. I have an example of map2. What I want to do is input 2 vectors of numerical values and sequentially index by index or element wise multiply the values that are contained in the 2 vectors. So here I have a vector 1, 2, 3 assigned to a variable x. Here I have a vector 2, 4, 6 assigned to a variable y. And I want to multiply 1 times 2, 2 times 4, 3 times 6. Map2 does that. And again, the sort of default behavior, or the base behavior, is to assign the output to a list object as opposed to an atomic vector. Okay, so you can see it. 1 times 2 is 2, 2 times 4 is 8, 3 times 6 is 18, and that's what we have achieved. So I hope that I have conveyed to you the sort of basic idea behind using the map family of functions to do iteration in the sort of functional programming paradigm in R. The next thing I want to do is present a series of sort of more interesting examples. So far, the examples I've provided are not very realistic in the sense of what you would do in most statistical applications or data applications. What I want to try to do is get at least one step closer to being like demonstrating actual use cases for what you could do and what you would be doing in day-to-day data analysis or statistics. And so my next goal is to show you a series of what I hope are more interesting examples illustrating the use of the map family of functions in R. So specifically, what I want to do is show you how to generate some simulated data and store that in a data frame. I want to show you how to standardize multiple columns in a data frame. And I also want to show you how to apply a t-test to multiple columns in a data frame. If, depending on what your background is, if you're not fully comfortable with some of these applications, I suggest just kind of try to follow the code. I think at least you'll get a sense for the logic of applying the map family of functions, even if you don't necessarily have a background to appreciate the specific application. Okay, so I'm going to go over to RStudio again and show you these applications. Okay, so again, you want to make sure that you have installed and loaded the tidyverse. For some of the more sophisticated examples that I have included in the code that I'm making available via the GitHub repository, I also use two other packages, but I'm actually not going to cover those more sophisticated examples in this lecture in detail, so I won't say too much about that. I'm going to set a seed just to make this exactly reproducible if you want. So the first thing I want to do is to ultimately create a data frame where each column is some simulated data, let's say simulated from a normal distribution. If I just apply the basic map function, I'm going to get a list. So the first thing I'll do is simulate a list with 5 entries, where each entry in the list is 15 numerical values sampled from a normal distribution with mean of 6 and standard deviation of 1.8. So let's look at what this looks like. If I print out my sim data, I have a list object, 1, 2, 3, 4, 5 components stored in the list. And each of the components is a vector of 15 numerical values that are sampled from a normal random distribution from with mean 6 and standard deviation 8. We said that our goal was to produce a data frame though. So one option is I can take each of these list entries and put it into a column of some data frame. However, it's easier to use the map underscore DFC, the C is for columns, to apply the simulation to columns in a data frame rather than a list object. So if I run this, I'll get a data frame. This tells me that the names have just been assigned to some kind of weird values. So what I'm going to do is apply the clean underscore names function from the janitor package to make that look just a little bit nicer. So this is not doing anything other than changing the names of the columns in the data frame. So now if I look at this, I have, instead of a list object, a data frame that contains 5 columns, 15 rows, where each column is a sequence of numbers sampled from a normal distribution with mean 6 and standard deviation 1.8. So this works pretty well for creating a data frame. What I said that I wanted to do next is to standardize each column in the data frame. That is, for each column, for each value in said column, I want to subtract the mean value and divide by the standard deviation of the data. So the first thing I need to do if I want to do this is to create a function that I'm going to apply to the data. So I create a function called my underscore stdzr. So that's my standardizer that inputs a vector. It then computes the mean, subtracts that from each value, and divides each value by the standard deviation. So I've created this function. Let's just see exactly what this is doing. So what I'm going to do is I'm going to apply my standardizer to just one single column of this data frame that I've already created. So I'll do my underscore standardizer of, let's say, the first column, and this produces the desired result. Okay, so now what I want to do is to do this for each column in the data frame. Well, I know that I have some data, and in this case, I'm going to output the result as a data frame. So I run that. What does this result look like? It looks like this. So why did I do the result as a data frame? Well, the input is a data frame, and I'm not summarizing the results, right? I'm applying the function, my standardizer, to each single column, to each single element in a given column for each column. So it makes sense for the result to be a data frame. Now I'm going to apply a t-test to each column in the simulated set of data in the data frame sim_df that I created. So I write a function, the inputs data, I apply a t-test using the t.test function in R. If you're not familiar with what this function does, you can always do t.test to call up the help documentation. It runs a student's t-test. I won't go through the details of what this is. The point is that I can extract the p-value from this t-test, so the significance of the result. And what I want to do is apply this function. Now, in this case, I'm applying a function of two variables to illustrate map2. Why? So when you apply a t-test, one of the parameters is what is the mean value, the hypothesized mean value. And perhaps I want to examine the results under a different hypothesized mean value for each column. So here I'm going to do a test for the first column with mean 6, a test for the second column with mean 7, the third column 9, 6, and 2 respectively. So let's see, did I call? Yes. So let's call this function, and let's look at what the output is. I get, because this is the just base map2, I get an output that is the a list object. Notice one thing, that since the input was a data frame, or at least one of the inputs was a data frame, which has associated with it column names, the names component of the data was preserved in the output to the list object. Okay, so the p-value for t-test to test if the mean of the first column was 6 is 0.45. So if you're familiar with the context, I would, in that case, fail to reject the hypothesis that the true population mean for that data was 6. Okay, and then there are some cases where it is significant and other cases where it's not. So the result's not that big of a deal. These are numerical values. These are double values. So I could have done map2_dbl and gotten a result that was not a list object, but a vector, although it still preserves, again, the names of the entries. So hopefully this gives some more sense of what you could potentially do with MAP. I have included some more sophisticated statistical applications in the remainder of the script, which I won't go over. Specifically, what I do is I show how to use the map family of functions to use bootstrapping to estimate standard error and confidence intervals for various statistics. Okay, so we've demonstrated the use of purrr, which is again a package that's part of the tidyverse that contains the map family of functions that facilitates iteration in R via the functional programming paradigm as opposed to the traditional procedural programming paradigm. If you want to learn more than what we've been able to explore in this lecture, I again recommend R for Data Science and Advanced R, and always the purrr documentation. There's a handy purrr cheat sheet available. Again, to click these links, you have to have the slides in presenter mode. I've put the code that I've illustrated here, plus some additional applications on GitHub. I just want to say if this is new to you, just give it some time. It can take some thinking and experience to get used to the map family of functions in R. I think what you'll find is that the more you use it, the more you will like using it, and the more you will see how to use it in practical applications when they come up. One of the strong reasons for me personally to use it is that it, one, helps to write cleaner code for sure, and two, it is programming in a way where you start to think so that programming for multiprocessing becomes much easier. So there's a package called purrr, I believe, so F-U-R-R-R, I think is what it's called. That's the multiprocessing version of purrr. The kind of key ideas that we have covered in this lecture are loops, the idea of for loops specifically in R, functional programming as another approach to iteration in R, and then using purrr to facilitate functional programming in specifically iteration via functional programming in R. So I really appreciate you taking the time to watch my lecture. Hopefully it's been informative and useful. If you want to get in contact with me, you can email me, and I'd be happy to try to provide additional resources and learning tools. If you're interested in this, I'm happy to answer questions and so forth. So again, thanks, and yeah, happy programming.